Hi everyone, my name is Emmanuel. I'm the PATS academic coach for chemistry. I wanted to try something new today with teaching. I know everything's been virtual and I'm sorry that I don't hold as many office hours as I'd like, but I wanted to try to do a video on, this is primarily for people who are in Chem 40A. I hope this works out well. I don't know, but we'll see. Chapter 4 is around cycloalkanes. You were introduced to alkanes and their nature in chapter, I think it was 2 to 3, where you learn how to draw skeletals and you learn that alkanes have rotation, free rotation, and stuff like that. So now we're going to be talking about alkanes in a ring formation, as you can see with these four molecules that we have here. I numbered it, so N is equal to the number of carbons, and then we have a ring strain here. So butane, pentane, hexane, and heptane, cyclobutanes, and then everything like that. So cyclobutane has 4 carbons, right, butane, and then it has a ring strength of 26.3. That means it has a lot of energy there, and it does not want that energy. It's not stable. As you go down the list and add more carbons, it starts to get a little bit lower. You can see this drastic 20 kilocalories per mole difference between cyclobutane and cyclopentane. But then you can see how cyclohexane here with 6 carbons is really the most stable, almost zero, almost neutral. So why is that? If you recall from drawing your Lewis structures, carbons typically like methyls or methanes and ethanes, carbons have an sp3 hybridized. So their bond angles between each substituent is around 109.5 degrees. And here I showed a picture of cyclopropane, which is a 3-membered carbon, considered to be one of the most unstable cycloalkanes. And as you can see, you can tell it's 28 kilocalories per mole compared to 26.3 and even compared to 0.4 of hexane. So knowing that the carbon wants 109.5 degrees of bond angle between them, I want you to take a look at the angles that are here, the angles between the bonds, as well as these orbitals. I drew it so that each color represents each carbon. This carbon has orbitals going this way, but it's also clashing with this orbital from this carbon. This is not a very good interaction to have. They're going to be fighting for the space right here. They want as much space as they can to freely move. And then you can tell by these bond angles right here, this is nowhere near 109.5. It's around 60 degrees. You don't have to know that, but you can tell this forms an acute angle. It's around 60 degrees, which is why they have such a high, they're not as stable as something as a cyclohexane. And if you were to draw out the cyclohexanes, you would see that each carbon has their own space to work with, which is why it is the most stable out of the many cycloalkanes. And in organic chemistry, we'll be dealing a lot with cyclohexanes. So you should be familiar and be comfortable with drawing these hexagons. And I'm sorry, mine are pretty disgusting looking. So you can, so from this point on, we're just going to be talking about cyclohexanes. And there are 2 different ways of, there's actually a few different ways, but in this class by far, we're going to be learning about, this is called a chair conformation, and this is called a flat ring projection. So a chair conformation is a way to 3-dimensionally see a cyclohexane. You can tell how this molecule doesn't really help me see 3-dimensionally what it looks like, right? And we draw it this way, not only so we can see it 3D, but actually this conformation gives you the least steric strain, steric meaning the groups coming off of it, the steric hindrance, and it also gives you the least energetical strain. So it's actually the most stable conformation. You can see how I drew one chair here and then another chair here. and we'll get to that later on. So with these shares, there's something called axial and equatorial positions. I grabbed this image off of Google. It's a 3D view of what a chair looks like. The red represents an axial group, and axial just means it exists above or below the plane of the molecule, right? So the red here is, we would consider this down axial because it's coming down, up axial, up axial, and so on and so forth. The blue here represents equatorial. Just think of it like the equator, sort of like a horizontal line, and it exists within the plane of the molecule. We would call this up equatorial. It doesn't look like it's coming down, but it is coming down. We would call this down equatorial, up equatorial, down equatorial. And if you start to see the pattern here, I'll show it in this, which I drew to be two-dimensional. I know it doesn't look that pretty, but it goes down, axial, up axial, down axial, up axial. So you know in your head, if this is down axial, this should be up, and then the trend continues. So down, up, right? And then since this is down axial, there's only one more space for it for the other substituent to exist, and that's as up equatorial. And if you know that this is down equatorial, up equatorial, down equatorial, and so on and so forth. I don't want you to memorize this, although it is very easy to memorize. I just want you to see the pattern here, how it goes down, up, down, right? Down axial, up equatorial, up axial, down equatorial. You can remember that in a few different ways, but I just like doing down, up, so that it gives me freedom to do the equatorials, as it is just the opposite. So even though I said that this chair is the most favorable conformation, there are multiple ways to develop this chair. And this is why chemists develop something called a chair flip. So if you can see this axial position and this axial position in 3D space, they occupy a lot of space. So therefore, bulky groups, they like to be in equatorial positions because there is less gauge, what would you call it? There's less gauge interactions right here, than the axial positions, so that they can occupy more space and be more stable in that conformation. So what happens in a chair flip? The direction does not change. So if it's up axial, it stays up. But what does change is the conformation. So if something was up axial and we flipped it, we did a chair flip, it's now up equatorial. And then I drew an example here. Here we have our original chair. I numbered the carbons right here. It's always going to be numbered this way, by the way. I would take a picture of this if you can, where our first group, again, was down axial. And take a look at, it was down axial and then up equatorial, right? And then let's compare that to this, where I did a chair flip. And then now the one carbon is over here at the top. This up equatorial became an up axial, okay? And then this down axial became a down equatorial. You see how the direction doesn't change, but the conformation does change, right? So knowing that, let's try an example of where we draw this molecule of the chlorines in a wedge. So I hope you can pause the video and try it for yourself, but I will just do it right now. Let's first number these. So I'm going to number them 1, 2, 3, 4, 5, 6, right? I'm going to draw it first in the original chair, which is, let's draw that a little bit better, which is like this, right? And then now let's number these. Oh, sorry, I drew it the wrong way. So it's like this. Yes, there is a way of drawing chairs, which is really, really weird. Okay, so let's number these carbons. I always like numbering the carbons. And then let's remember that this was a down axial, right? Up axial, down, up, down, up, right? But I'm not going to do that right now. I'm just going to focus on these chlorines. So in a wedge, it means it's pointing up, right? And it's on carbon number 1, but we know carbon number 1 has a down axial position. The only up is in equatorial, so then this chlorine would be in an up equatorial, right? And then let's do number 3. So this was, let's just do the hydrogens here. This was up axial hydrogen here, down equatorial hydrogen there. And then we get to 3. Okay, this is again pointing up because it's a wedge. So we did up axial for this. That means 3 has a down axial position. And then it means the chlorine will now be in an up equatorial like that. And we can fill in the rest where it goes up axial, down axial, right there, and then up axial. You don't need to join all the H's here. What's more important are the chlorines, right? And then now I'll draw in a chair flip. So a chair flip is going to be the other way, how I drew it before, where I had it this way now, right? And then the 1 starts up here, 2, 3, 4, 5, 6, right? So now there's a couple ways to do it. You can do it again for each carbon here, but I know that in a chair flip, the direction stays the same, but the conformation changes. So I can see here that at number 1, this chlorine was an up equatorial. So then if I flip the chair, the chlorine should stay up and it should be in an axial position, right? And then we can go on, but then we can get to 3 here where it's up. This is up axial, down axial, and this is up axial again. And then I know then from this conformation here, the chlorine was in an up equatorial, and in a chair flip, the direction stays the same, but the equatorials flip to axials, and then axials flip to equatorials. So then this chlorine would be in an up axial position, right? So which chair is more stable? If you recall what I said previously, bulky groups like to be in an equatorial position than in an axial position because there is more gauge interactions in an axial position than there are in an equatorial position. So by that case, these two groups are in up axial positions. It may not look like it now, but in 3-dimensional space, these groups are interacting with each other really, really strongly. So we don't really, that's not really favorable for this chair conformation. So we can see that this has an equatorial, both of them are in equatorial. That means they both have less gauge interactions, which means this chair is the more stable between these two. Okay, I hope that was able to help. Feel free to reach out to me if you have any questions about the material. If you like this, I'll probably be making more. The next one is stereoisomers, which I really enjoy. But I hope this was able to help you, and I hope your studying goes well. I'll see you all